Hello and welcome to this presentation on DirectX Lighting. Up until now our scenes have not had any light interactions. The color of objects is dependent on the color of the vertices that we set that is then interpolated across the surface of a polygon. Today we're going to modify those colors to allow for lighting to be computed and different lighting effects to change the color of a surface. We'll start out with a little bit of math. In particular, one of the key things that we need to add for lighting calculations is what we refer to as a normal. So if you recall, a vertex can have a variety of properties. The two properties we've used so far are the position, the world position XYZ, and the color of the vertex. Vertices can also have a normal, which is a direction vector that's perpendicular to the surface, and it can also have a texture coordinate, which we'll see a little bit later in the course. To compute a normal, again, a normal is a direction vector that's perpendicular to a surface, and for a polygon you can compute a normal by taking the cross product of two edges. So if you take the vertex B minus A, you'll get edge 1, and then if you take the vertex C minus A, you'll get edge 2, and then if you take the cross product of edge 1 and edge 2, you'll get a vector that's perpendicular to the surface. It's also common to normalize these normal vectors so that they have a length of 1. That makes the calculations a little bit easier in lighting. For some shapes, like spheres and cylinders, and perhaps some others, we can calculate normals a little bit differently. In particular, for a sphere, if we take the surface point, say P, and subtract the center, we will get a normal vector. And again, we should normalize that vector to get the right direction. So the normal for a sphere is always the surface point minus the center. So the normal for the sphere is always pointing outward away from the center. For transforming normals, so for example, if we have a object like our cube that is at the origin and oriented so that it's aligned with the major axes X, Y, and Z, if we were to transform that cube, like scale it or rotate it or move it around, especially if we rotate it, then the normal for the top face of the cube would no longer be the y-axis if we rotated it. So we have to be able to transform the normals, and if you recall from our math presentation previously in the course, we talked about how we transform a normal by making some changes to the world matrix. So if we take the world matrix and zero out the translation components, and then compute the inverse transpose of this matrix, that's the matrix that we want to use to transform normals. That leaves us with just the rotation parts that we want. Another bit of math that we'll use is a little bit different type of vector multiply. So we've seen, for vector multiplication, we've seen vector scaling, we've seen a vector dot product, we've seen a vector cross product. Here we're going to see what we call a component-wise product, or in some textbooks or references they call it the Hadamard product. Basically, we just take all the components X, Y, Z, and W and multiply them together. And we use this symbol, the book uses this symbol. I'm not sure how common it is outside of our textbook, but I'll try to use it as well. And that's a circle with a cross in it. So this is not cross product, but this is component-wise multiply. And basically we just multiply all the components together. AX times BX, AY times BY, AZ times BZ, and AW times BW. And that gives us the new X, Y, Z, and W components. And this multiply could be done in 2 dimensions, 3 dimensions, in this case 4 dimensions when we're dealing with color. When we're dealing with color, we have a red, green, blue, and alpha component. Sometimes we'll use X, Y, Z, W interchangeably with RGBA. The next thing we'll look at is what we call common light interactions. So how do lights interact with materials? In the real world, the physics of light material interactions is rather complex and varies based on the spectrum or based on the color. So in computer graphics, we tend to model or simplify this interaction by coming up with a lighting model that gives us some decent results, but is not overly complex and doesn't involve too many calculations. There are more advanced lighting techniques such as ray tracing and radiosity that can be used, but they can be very computationally expensive. So these are some of the common light interactions and light models that are used in computer games. The first 3 components we'll look at, or the interactions we'll look at, are ambient, diffuse, and specular. So ambient light is what we refer to as the general level of light. It's light that's bounced around off of walls and surfaces so much that you don't really know where it's coming from. You can't tell where it's coming from. So you see in the diagram here on the left, the teapot with ambient light, all the sides of it are the same level of lighting. And so this is really boring, but at least we can see something, and it gives us an indication when there's more interesting types of lights. It gives us an indication as to what is the backside. It's not completely dark, but it's not lit by other types of light, and so you can see this backside. And so normally ambient lighting is a kind of a small, a weak component of our overall lighting model, so that it's not completely dark, but it's not very bright either, and it gives us an indication as to the backside or the unlit side of an object. Diffuse lighting is light that has a particular direction, and when it strikes a surface, the surface is not terribly smooth, so that the light bounces off, reflects off in all directions. And the diffuse lighting is commonly modified based on the angle between the light vector and the surface normal. So the arrow pointing to the left here would be the surface normal for this wall or surface, and the light direction coming in, that angle is used to compute the intensity of those reflections. So it works out fairly well when the light is aligned with that normal to make it brighter, and when the light is perpendicular to that normal to make the diffuse component of the light to be very small. And that ends up giving us a fairly nice view on curved surfaces. And you can see here on the teapot the diffuse plus the ambient. You see on the back side or the bottom side the unlit areas, you see the diffuse component. It's not completely dark, but it is fairly dark. And then on the upper components where the light is hitting the curved surface, you see how it gets brighter and falls off as we move away from the direction of the light. So as the angle between the surface and the light increases, the contribution of the diffuse light becomes less and less. It gets darker and darker. The last part that's added here is the so-called specular component. And with specular light, this occurs with particularly shiny surfaces, mirrors and car windows, even the surfaces of cars that are polished really nicely. What happens is the light vector strikes the surface and it reflects off in not all directions but a single direction. For a perfect shiny surface like a mirror, it reflects off in a single direction. For a surface that's really smooth but not perfectly shiny like a mirror, it'll reflect off in several directions but in the same general area as the reflection vector. And so we can compute the reflection vector, and we also take into consideration the position of the camera. And if the reflection vector is going right to the camera, then we see this really shiny bright spot like the reflection on the really bright reflection off of a car windshield, or even a shiny curved surface like an apple. You see this fairly common. And so here in this image on the right, you see the specular reflection here, the really bright spot, and you can also see it a couple places here on the spout of the teapot as well. And so normally in our games we want to try to come up with a model that includes a certain amount of ambient, diffuse, and specular light interactions, and it makes for a little more realistic looking scenes. Some of the equations that we see range from fairly simple to fairly complex. The ambient light equation is fairly simple. We come up with this Ka, this factor, the ambient light contribution, and it's this component-wise product of the ambient light RGB value with the ambient material RGB value. So not only do we have a light that's made up of an ambient color, but we also have a material for a surface or an object that is also made up of an ambient color. And so the ambient color of the material, if it were red, it might have a value of 0.700. The ambient light, if it were white, again, we don't want a very large contribution, so we might give it a value of 0.3, 0.3, 0.3. So 111 would be white, or 111 RGB would be white. But if we don't want a very large ambient component, we might make that ambient light to be 0.3, 0.3, 0.3. And so we'd get the G and the B values would multiply by the G and the B values of the material, which would be 0, 0, so we would not get any blue and green. The red component would multiply by the red component of the material, so we would get some red contribution to the ambient light interaction. The diffuse interaction is a little bit more interesting or challenging, and that involves computing a diffuse factor that's based on the dot product. So again, for the diffuse lighting, we want to know the angle between the light vector and the normal vector, and we can do that using the dot product. And this is often you may hear the phrase what they call N.L lighting or L.N lighting. So we take the light vector and compute the dot product with the normal vector, and if both those vectors are normalized, the result is related to the angle between these. So it's actually the cosine of the angle. So if the light vector and the normal vector are parallel or the same, then we get a 1, and if they're perpendicular, we get a 0. So 1 would give us a full diffuse contribution, and a 0, if they're perpendicular, would give us no diffuse contribution, and that's what we want. So it's very common that we use this type of equation to compute the diffuse factor. We use the dot product between the light vector and the normal, but we want to clamp it at 0, so the dot product can be negative if it goes beyond, if the light vector were down here, we would get a negative dot product, but we don't want to go below 0, so we use this max function to clamp the diffuse factor between 0 and 1. Then we take that diffuse factor and we multiply it by the scale, the component-wise product of the diffuse light color and the diffuse material color. The next one we'll look at is specular lighting, and it starts out somewhat similar, but there's a significant change. And the big change is that we compute a couple of different vectors. One, we compute a reflected vector we call R. So this is the reflection of the light vector about the normal. And when we compute the reflection vector about the normal, we want to know the angle between this reflected vector and what we call the I vector or the view vector. Sometimes they use V to represent the vector from the surface point to the viewer or the camera. So then the specular factor is V dot R is related to the dot product between V and R. So if R is the same as V, then you're looking right into the reflection of the light and you see a really bright specular component. As that angle increases, you see less and less of that specular component. And typically the equation that we use for this is something like this. We take V dot R and clamp it to the range of 0 to 1 with the max of 0, and then we raise this value to some power P we call the specular power. And that power P is normally actually fairly large. It's normally 5 or 10 or more, sometimes between 10 and 20 some. Gives you a fairly good value for the specular reflection. Something else that we do is we place this within a max or an if statement if L dot n is less than 0. So if this light vector is coming from the back side, then we don't want to compute any specular contribution. So we'll do another calculation on the L dot n, and if it's greater than 0, go ahead and compute the specular factor. If it's less than 0 or on the back side, then we won't compute any specular contribution to the light. So the specular component is a little bit more complex, but it's similar math involved. The big difference is that we add in this reflected vector and we add in this I or view vector, and we want to know the angle between that instead of the angle, or in addition to the angle between the light vector and the normal. So now we understand some of the calculations involved in creating these lighting effects. A question comes up, where do we put these calculations? And We have at least a couple of possibilities. One is we know that the vertex shader can allow us to perform calculations for each vertex, and the output of the vertex shader can include a color component. So that's one possibility, is to put these calculations in the vertex shader. The problem is we would just be computing the lighting contributions and the lighting color for each vertex, so that if we have a polygon and we only compute the light for each vertex, we would only have 3 colors or 3 lighting values, and then those colors would be interpolated across the face of the polygon in the pixel shader. And when you do that, in the extreme case, if all the lighting calculations are the same, you get this flat shading that you see here, where every polygon has the same normal, and so every polygon has the same color. If the polygon's vertices have different normals, as they should on a smooth surface, it will look a little better, but you'll still see this odd effect, especially in the specular component, because the lighting is not, maybe the specular component should be bright in the center of the polygon, but we're not computing it properly. Or maybe it should be bright across 2 different polygons, but we're computing the lights here at the vertices, not where the specular is actually at its brightest. So you can get these odd effects due to performing the calculations in the vertex shader on a per vertex basis. A better solution, although it's more computationally expensive, is to perform these lighting calculations in the pixel shader. And this is what we see here in the teapot on the right. You see that we get a nice, smooth, round specular contribution to the light. Not only here, but you also see it on the handle, and you also see it a little bit on the spout of the teapot, and you see that it's a much smoother, more realistic looking specular reflection than when we do the lighting calculations on a per vertex basis. So again, this is more computationally expensive, but thanks to the processing power of the GPU, it can be done fairly quickly. The next thing we'll look at is actually the different types of light. We've seen different types of light interactions, but we can actually have different types of light to represent different types of lighting that you might want in scenes. So the first is ambient. We've already talked about that. It's a very simple, constant value of lighting, and we usually keep that fairly low. The next one is directional or parallel, and this is lighting where all the light rays are parallel to each other. So this is light that comes from so far away that you can't tell what direction, you can't tell the exact point in space where it's coming from, because all the light rays are parallel. And although you may think of the sun as a point light source, and in the big picture it is, but with our scenes, outdoor scenes, the light that we receive from the sun is fairly much, those light rays are fairly much parallel because of the huge distance that the light has traveled across. So outdoor lighting is generally best, daytime outdoor lighting is generally best represented with what we call directional or parallel lighting, where all the rays are parallel to each other. And this is a simple light to implement because we only require that the light ray has a direction vector, and that's that direction vector is the light vector that you see here and the burgundy light vector that you see here. So that would be that would coincide with the direction vector of a directional light source. Another type of light that we have is a point light, and this is if you had a bare light bulb, so if you had a lamp and you took the shade off of it, so you had a light bulb, that bulb could be considered a directional light. It emits light pretty much in all directions. And this is what we refer to as a point light source. The point light source has a position in space, but does not have a direction. The direction is everywhere, and so when we do the calculation at a particular point, say A, then the light direction in that case is going to be the point A minus the position of the light. So we compute the light direction for a point light as the position on the surface that we're considering minus the position of the light. And we have to make sure that we're doing this subtraction, computing this displacement vector in a consistent space, whether it's local space or world space or probably not screen space. Most of the time this is done in world space. So we have to make sure that we transform our surface point by the world transformation matrix before we do this subtraction. Both directional and point lights can have diffuse and specular components, whereas ambient lights do not have any diffuse or specular component. They just have a ambient component. Another common type of light is what we refer to as a spotlight. If you think of a flashlight or a headlight on a car, a spotlight has both a position and it has a direction that it's aiming at. And it also typically has some type of angle that gives you an indication as to how wide or how narrow the beam of the spotlight is. So if you can imagine a spotlight with an extremely narrow beam, you'd have something like a laser. Or if you think of a spotlight that you might see at in a theater or up on a stage, you might have an angle of a few degrees, 5 degrees, something like that. Spotlights also can have diffuse and specular components. And we have to modify the specular component a little bit to take into consideration the cone angle. So normally what we do is we have some type of fall off in intensity from the center of the spotlight to the edge of the spotlight. So typically around the edge of the spotlight it's not quite as bright as it is in the center. And once again, it's common for us to use the dot product. We can take the surface point and subtract the spotlight. So if we had a surface here and we take this surface point and subtract the spotlight position, we would get this vector. And we might call that L. And then we have the direction of the spotlight. We might call that D. And again, we can use this dot product raised to some power to give us a scale factor for the intensity of the spotlight at that point. And it's common to use a power of around 5 to 8, which would simulate a particular cone angle for our spotlight. And you have to kind of play around with that to get the right angle that you want for your spotlight. One final comment to make on the math behind lighting is what's referred to as attenuation. So for lights that have a position, like point lights and spotlights, it's not uncommon to attenuate the light based on distance. So if a light that has a position, like a spotlight or a point light, is farther away from an object, then it may have less of effect than a light that is closer to an object. And so you can see here see in the image here, the light that's closest to the ground has a greater effect than the light that's furthest away from the ground. And this is due to attenuation factors. Normally the attenuation factor is a scale factor that's computed something like this: 1 divided by, and then in parentheses, some constant plus some constant times distance plus some constant times distance squared. And normally we don't use the first one. Normally we don't use this first one, A0. Normally that's 0. We don't bother using that. Normally we use an attenuation that's either based off of distance or based off of distance squared. And if you look at the graph of the two, you can see the difference between them. The graph of 1 over r squared is the red one, and you can see that as you get close, less than 1, the value increases a lot, and as you get far, it decreases very quickly and gets really small very quickly. The graph of 1 over r, in contrast, doesn't increase and decrease quite so much, so you get more of effect over a long range of distance, and this is probably the more commonly used component of attenuation. So you can see we have a variety of math components surrounding ambient, diffuse, specular lighting for different types of lights like directional, point, and spotlights. And it can be fairly challenging to implement this. So let's now look at some of the code changes that we need in order to implement this. Here's a scene that's produced by the sample code that's in the file section of our course, and in the scene we have a terrain that doesn't look like it's lit at all. We have a couple of pyramids, and you can see the difference in the lighting. Here this face of the pyramid is brighter, and here this face of the pyramid is darker. And notice that the entire face is going to be the same color because the normal is the same for that entire face. So here it's darker, here it's brighter. So this indicates that the normal pointing up must be somewhat perpendicular to the light source. Here you see a similar effect on a round surface like an egg type shape. This is actually a sphere that's been scaled non-uniformly, so it's a ovoid or egg type shape. And you can see that we have what looks like it might be a specular component here, and then maybe diffuse lighting as we go across here, and then you can see the ambient lighting in the back, the lower level of lighting in the back. So how do we implement this type of changes in our code? One of the first things that we have to do is to compute normals. So if we look in our polyObject class, we now have a data type called vertex position normal color. And if we look at the definition of that, you can see that we've added a float 3 for normals. We still have the position of the vertex, but now in addition we have a normal capability. So when we set the input layout, or the layout of the vertices, we have to be sure to set the appropriate format or layout of these vertices. And so this section here is very important. We have the semantic position that's a 32-bit RGB, in our case it's XYZ, 32-bit float, 3 channels. In the next position we also have a 3-channel 32-bit float, but it's for normal. And then the final component is color, and that stays the same. It's a 4-channel 32-bit float for RGBA. And so this is an important change based on the vertex type that we're using for our poly object. It's very important that that vertex type match up with this input layout or vertex descriptor that we set. One of the next changes that we'll look at is the addition of a sphere object as a poly object. So in our poly object class, we've seen functions where we can add a vertex, a triangle, add a transform, and we saw previously how we inherited or derived from the poly object class to create a terrain class where we used a set of loops to create a tiled flat surface, and then we talked about how we might use different functions to raise or lower that surface to create hills or different features using a height field or a function, something like that. Now we have the capability, and I believe that I took this code from derived this code from our textbook by Luna. We have the ability to create a sphere, and when we create the sphere, we're going to create it with lines of latitude and longitude I'm just trying to grab an image that might be useful to us. So what we're going to do when we create the sphere is we're going to divide up the sphere into lines of latitude and longitude as we do on the Earth to specify coordinates on the Earth. And so the latitude lines run horizontally or create a series of stacks, sometimes they're referred to as stacks, on the sphere. And so those lines are going to be parallel to the x-axis. The longitude lines are referred to as slices, so you can think of slicing up a pie based on a certain number of angles. So we have certain longitude lines that run from the North Pole around the surface to the South Pole and then back up on the other side. And so those lines of latitude and longitude then we can use to create polygons by making a diagonal there, and then now we have at the intersection of latitude and longitude lines we have 4 vertices, and we can use those 4 vertices to create 2 triangles. So the code change for it starts with defining the top and the bottom vertex, and then we take our vertex list and we start at the top and push in the top vertex. The steps that we use are based on pi over 180, so that gives us the stacks that we're going to use, and that's actually half, so the number of stacks is in either the top half or the bottom half. And then the number of slices are 2 pi over the slice count. So we've already added the top vertex, so then we start our loop from not from 0 but from 1 to stack count, and we compute the actual angle phi for each stack. So the angle phi is going to be the angle from the y-axis down to the line of the particular line of latitude, and then the angle theta is the angle around the circle in the XZ plane. From there, we use a very common transformation going from spherical to Cartesian coordinates. You may have seen this previously in an algebra class or trigonometry class. And this gives us the X, Y, and Z position of that particular vertex. The next step that we talked about is we have to compute the normal. And the normal is going to be, in our case, the position of the sphere minus the center. But what we've done is we've created this sphere centered about the origin, so the center is 0, 0, 0, so we don't actually have to do the subtraction. So our normal is just the position on the surface normalized. So this gets us the normal at that particular point on the sphere. We're not concerned with texture coordinates right now. We'll look at those a little bit later. And the color, we made this sphere, for now, we made the color of the sphere just have a red component. It turns out we're not actually using the color component of the vertex. Instead, we're using the color component of the material that we set, the ambient, diffuse, and specular material that we set for this object. And for each of these steps in these two nested loops that go, the outer loop is the stacks, so that's the latitude. The inner loop is the slices, so that's the longitude step. For each of these steps, we push back that vertex position, and normal is the key part. When we're finished with that, we start from the bottom and do the same thing. Oh, excuse me, when we're finished doing all these vertices, we push in the bottom vertex. So we've done all the stacks for all the slices, and we add in the bottom vertex. Now we have to add in the indices. So if you remember, the vertex buffer also needs an index buffer, and we need 3 indices for each triangle. So we put in the first 3 indices, and that's the one at the top at the pole. And then we go through the slices and the stacks, and we compute the indices for each 2 triangles at these intersections. And this is not much different from what we did with the terrain. The math is very similar to what we did with the terrain. We need to figure out where we are in stacks or latitude, and where we are in slices or longitude, and then compute those 4 vertices and put them together to create 2 triangles. When we've done all those, then we also compute the indices for the South Pole as well. And this is essentially, the North and South Pole is very similar to slicing up a pie. If you look at it from a top-down view, it looks like the slices of a pie. So we just need a single loop going around the slices to do that. So that allows us to create a sphere within our scene, and then by scaling it non-uniformly, meaning have different scale factors in X, Y, or Z direction, we can create an ovoid or a football type shape, an ellipsoid type shape, maybe an egg type shape. The next thing we need to include in our code is the material. So in our header file for the poly object, we've added a material. And if we go to the definition of this material, I put this in DX11 util.h. We define the material as having three properties: an ambient, diffuse, and specular color component. So we use the RGBA 4-channel color component for each of the ambient, diffuse, and specular components of a material. So this allows, by putting this material in the object class, it allows each object to have a separate material associated with it, and it can have different colors, and it can also have different colors for different light interactions. So you could actually have a material that may not be very smooth, and so you could set its specular component to 0. You may have a material that's extremely smooth, and so you could set its diffuse component to something very small and a specular component to something very large. The next thing that we'll add is a particular type of light, and something more interesting than just an ambient light. And so we'll create a directional light. And our directional light will have an ambient, diffuse, specular component as well as a direction. And it might be more realistic to take the ambient component out and make it a constant for the entire scene rather than for this particular light. But in this example, we created the directional light to have an ambient, diffuse, and specular color components, and they will interact with the ambient, diffuse, and specular components of the material. And because it's a directional light, we'll also have a direction. If this were a point light, instead of a direction, we'd have a position. If this were a spotlight, instead of just a direction, we would have a position, a direction, as well as some type of angle or power to have that fall off based on the cone of the spotlight. The next part we need is the shader data. And because of the additional light calculations, we need a little more data being transferred to the shader program from our CPU. So you see here we've got a class for shader data, and we need several transformations. We need the world transformation matrix just by itself, and the reason for that is to compute the world position of each vertex that's coming in. We need that position in order to do certain light calculations. The other one we need is the world inverse transpose, and as we discussed, we need that in order to transform the normals to world space. And then in order to take those vertices and compute them to screen space or homogeneous space, we need the world view projection matrix. So there's several transformations that we need. The world view projection is the one that we've used in the past, but now that we have normals to transform, we need the world inverse transpose, and for certain lighting calculations, we need them in world space, so we need just the world transformation matrix. We're also going to pass in the directional light, and we're also going to pass in the world position of the camera. So that you can see that this shader data has a corresponding structure in our shader code. So we have, instead of a matrix, we've got a float 4x4. Well, that is a matrix. We have those for those three transformations. We have a material, we have a directional light, and we have a float 4 for the camera position. And notice that the material and the directional light structures match up with the types used for the material and the directional light in our C++ code. And so that's the shader data that's passed in. The other additional code is the actual calculations in the shader. And in particular, we took the function compute directional light from the Luna text and maybe made a few changes to names, a couple of changes. But the idea is that we're going to take in a material, we're going to take in a directional light, we're going to take in a normal, we're going to take in the v vector or the 2i vector, and we're going to output ambient, diffuse, and specular calculations for this directional light. So the light vector is just the XYZ component of the directional light, and we flip it or negate it so that it's pointing in the opposite direction, pointing toward the light rather than toward the surface. The ambient component is just the component-wise multiply, so in the high-level shader language, the asterisk is defined for multiplying two vectors, and it's defined as doing a component-wise multiply. And that's what we need to compute the ambient component. The diffuse factor is this L.N lighting. That we've seen, and we only want to use it if it's greater than 0, and also if it's greater than 0 we want to compute the specular component as well. So the light vector that's moving toward the surface is reflected about the normal, so high-level shader language has a reflect function, and that gives us the reflected vector. And then the I vector is passed in, so that's the camera position in world space minus the surface point, the vertex position in world space. And so our specular factor then is the dot product of the reflected vector and the I vector. And we limit that to ranging between 0 and 1. We get the specular power that we're going to raise this to, so we're going to raise that to a power, and then we're going to get that from the material specular W. So we don't use the W component of ambient, diffuse, and specular, except somehow we need the power to raise it to, and so we store it in the specular W component. And we want it to be, we don't want to raise it to the 0 power, so we want it to be the larger of whatever that specular component is, or 1. And then this gives us the specular factor that we need. So now the diffuse and specular components are computed by the component-wise multiply of the material and the light, and then because this is a scalar, then this is a scalar multiply of the diffuse factor and the specular factor. So this function computes the directional light, the ambient, diffuse, and specular components of a directional light computation on a single vertex, a single position that's passed in. How does that fit in with our vertex and pixel shaders? Notice that the input vertex is position normal color, and this matches up with our data type here for position, normal, and color for each vertex. So that's the input to the shader, to the vertex shader. The output of the vertex shader has two different positions. It's got the position in screen space, or the homogeneous space. It also has the position in world space, and the reason for this is we need to be able to do the lighting calculations on a per pixel basis, so we need to send that information to the pixel shader. We also need the normal in world space, and the color, we're not really using the color for the vertex, so this probably isn't necessary. It's just left over from what we had before. So the vertex shader takes the local position of the object and extends it to a four-dimensional vector and multiplies it by the world transformation, and then takes just the XYZ component and stores that. The screen position is done as we've seen before. Take the local position, extend it, multiply it by the world view projection matrix. The normals in local space are multiplied by just the 3 by 3 part, because remember we just want to include the rotational part and the scaling part of the inverse transpose. So the normals are the world normals are computed a little bit differently. And those are the three components that we want for output. The color is not even used, so we're not even setting the color. It probably should be taken out of both the vertex definition, the vertex in, and the vertex color, but it's left over from before. The pixel shader then takes all this information as input, so the input to the pixel shader is the output of the vertex shader. And the first thing we do is normalize the world normal. We compute this eye position, this eye direction. So this is the camera position minus the vertex position. We're going to sum up a series of colors, both from ambient, diffuse, and specular components. So we start out with initializing those all to 0, and then we compute contributions from each light source. We only have a directional light in this case, so we're just computing, calling that function to compute the contribution of that directional light to our ambient, diffuse, and specular component, and then we add that to our ambient, diffuse, and specular color. The final color then that we're returning is the sum of all those components. So we took the contribution from each light source, in our case we only had one, added them into, separately added them into ambient, diffuse, specular components, and in the end added those all together. So you have to be a little careful with when you start to add in multiple lights, in that if you have two lights that are fairly bright, they can saturate the scene and make everything full intensity, and you can't tell individual lighting contributions. And you can reduce this potential problem with attenuation or by adjusting the intensities of the lights when you start to add more than one light. When we run this, we'll see the scene where we have a flat surface. So you can see, well, actually the surface is not flat. You can see the surface is wavy, and we'll discuss why it looks flat in just a minute. You can also see pyramids and this egg oval shape rotating around, and you notice the lighting changing on the surface of the pyramids pretty dramatically because they're flat surfaces, and as they point to the light source, the surface that's pointing toward the light source is much brighter than the surface that's perpendicular or pointing away from the light source. You see a similar situation that occurs on the oval shape object, where you can tell that the light source is coming from in front of us. The camera, we can move the camera around. So if we go look at the back side, you can see the diffuse component on the back side of these objects, and you just get a glimpse of the brighter specular, you see the ambient component on the back side, and you can see a glimpse of the brighter specular and diffuse components on the other side. And you can see similar type effects in eclipses and things. So I guess the final question to ask is, why does the terrain look flat? Why doesn't the terrain look lit? And if we go look at the code for the terrain, there's a function here called getTerrainNormal. And if we go to the definition of getTerrainNormal, you can see that the normal is computed as a constant. And for a flat surface, that's the case. The normal's straight up. But in our case now, we have a curved surface that's computed with cosine function, or a combination of sine and cosine function. You can play around with different things. So how would you go about computing the normal for a curved surface? And the way to do that is to find 3 points, just like we had 3 points of a polygon. Find 3 points that lie on the surface or very close to the surface, and take the cross product of 2 of those points with other 2 of those points. So if I can pull up the diagram from the presentation on terrain, if you recall, the terrain was created just as a grid of squares and then converted those into polygons. We could compute the normal at each vertex simply by taking the edges of the vertices and do the cross product with them. And that would work okay as long as the triangles are not too large. One potential improvement that might be more accurate is at each vertex, take the point that's the vertex and then step away a little bit in the x direction and step away a little bit in the z direction, and get those points, create a vector from that, create a vector in the vertical direction, and do the cross product on points that are much closer together, and that would give you a more accurate normal. So you can compute the normal with the cross product of the 3 vertex points. The problem with that is all the normals will be the same, and we know on a curved surface they shouldn't be the same. So a more accurate approach is to take points that are closer to the vertex, one in the x direction and one in the z direction. So you can just take the current x value and add something really small like 0.1 to it, and take the vertex position and add a z value of 0.1 to it. Find out what that, call the function get terrain point on those x and z values to get the actual x, y, and z value. So we move a little bit in x, get a terrain point, move a little bit in z, get a terrain point. We've got the vertex point, so now we have 3 points that we can use to do a cross product and get a normal. And by moving in a much smaller distance from away from the vertex, you'll get a more accurate normal calculation. So that concludes our presentation this week on DirectX lighting. I'm looking forward to seeing what lighting effects you'll be able to produce in your work this week. Let me know if you have any questions.